Today we're taking a look at section 8.2. We've got several objectives we'll be working through. First of which is to compare the different coordinate systems. We will have three in total: the rectangular coordinate system, polar coordinate system, and complex system. So we're going to start off by looking at graphing complex numbers in an Argand diagram. We'll write complex numbers in the rectangular format as well as polar format. And then we'll take a look at operations, specifically multiplying and dividing complex numbers in polar form as well as rectangular form. And then we'll also learn about a useful shortcut called De Moivre's theorem to evaluate powers of complex numbers in the polar form. Then the extension of that would be to take a look at roots in this situation as well to wrap things up. All right, so getting started, just quite simply taking a look at an Argand diagram. An Argand diagram is just another name for the rectangular coordinate plane. So when we update our rectangular coordinate plane, our x-axis is referred to as the real axis, and the y-axis is referred to as the complex axis. So if you look down below here, I've got 4 examples that we're going to plot points in this Argand diagram. First thing I'm going to do is add some scales to the graph. Okay, so the very first one, I'll go ahead and color code these so you can keep track. I've got Z, and Z is signifying that we have a complex number that we're going to work with. So Z equals -3 plus 2i. The first number is telling us which way to move on the real axis, and the second number, the 2, is the coefficient for the complex term, and that tells us which way to go, either up or down. So start at the origin like you are used to doing. We're going to go 3 to the left, and then we're going up 2 units. I'm going to place my point, and then I'll just go ahead and label it Z equals -3 plus 2i. I'm labeling it because I'm going to graph 4 of these, and so I'd like you to be able to see which one's which. Okay, example B, we have 0 plus 3i. This could also be written as just Z equals 3i. But 0 is your placeholder that says do not move left or right, but +3 tells us to go up 3 units on the complex axis. So I'm plotting my point, and I'll go ahead and label that Z equals 0 plus 3i. Next one, we've got Z equals 5 minus 4i. So we're going to go 5 to the right from the origin and go down 4 units, and I'll label it. And last one here, we have Z equals -4. So this one has an alternative way of writing it. If you want to put placeholders in, this is technically -4 plus 0i. So we're going to go 4 to the left, and we're not going up and down. Okay, so that's all there is to graphing complex numbers. Just recall that the x-axis is our real axis, and y-axis is the complex axis. Okay, what we're going to do next is work with converting. So the first few examples here says we're going to express each complex number in the rectangular form. So when they tell me I'm going to rewrite the complex number rectangular form, I need to make sure I know my format. I'm going to start with Z equals x plus yi. Okay. And also, you want to make sure you're recalling that to interpret our complex polar form that they gave to us, you may find it helpful to just write it down below. Z equals R cis theta. Okay, so from here, I just want to recall that I have formulas that I can utilize here to help me determine my information. X equals r cosine of theta, and y equals r sine of theta. And we'll just take our information and calculate both of those. So x equals r, which is 4 cosine of 45 degrees. This is unit circle based, so we'll go ahead and just evaluate like that. Plug in radical 2 over 2 for cosine of 45, and then simplify, and I end up with 2 radical 2. Okay, then for the y value, y equals r, so 4 sine of 45 degrees. So y equals 4 times radical 2 over 2 as well. And that is 2 radical 2 once you simplify. So that rectangular form then, z equals x plus yi. I'm just plugging in what I know. The x value is 2 radical 2, and the y value is 2 radical 2. You will probably see me, if I have to write something after my radical, put a little hook on there just to communicate nothing else is under the radical with the 2. Okay. If you're comfortable utilizing our formulas, you're welcome to pause the video, try the next example, and then resume the video to see if you got the right answer with me. So I am going to go ahead and just copy down my formula. Afterwards, I'm going to start the conversion. So x equals 5 times cosine of 90 degrees. I know that from the unit circle, cosine of 90 degrees is actually 0. So we get 0 for x out of that. For y equals 5 sine of 90 degrees. So y equals 5 times 1. So we get 5. For the complex rectangular form, remember z equals x plus yi. The placeholder for x is 0. And of course, y is 5. So you could simply write just z equals 5i. Both of those are good answers. Okay, number 3. Again, you've got z equals r cis theta. So you can see exactly what is r and what is theta. For x, remember that is r times cosine of theta. So we have 6 times cosine of 120 degrees. We know that's on the unit circle, so we're going to plug in what we know. Cosine of 120 degrees is negative 1/2, and that gives us an x value of negative 3. For y, we have r times sine of theta. So y equals 6 times sine of 120 degrees. Again, from the unit circle, sine of 120 degrees is radical 3 over 2, leaving you with a y value of 3 radical 3. Complex rectangular form, z equals x plus yi. So we've got z equals negative 3 plus 3 square root of 3. I'm going to close that radical times I. All right, one more. I'm not going to scroll this yet, but notice every angle we've had so far has been unit circle based. So this time we're going to need our calculator, because notice 47 degrees is not unit circle information. So we still do everything the same. I would want to compare this to z equals r cis theta. Formula is still the same, x equals r cosine of theta. And we'll go plug that in. Our numbers, so 3 cosine of 47 degrees, and then we'll need our calculator. I'm going to go ahead and set up my information for sine, y equals r sine of theta, just so I can just go to the calculator and do both of them one right after the other. So y equals 3 sine of 47 degrees. And I'm going to scroll back up top. I can't remember if I gave us rounding directions or not. I did not. So, if you are unsure and you want to play it safe, 3 decimal places are always sufficient. And I'm going to need to grab, go get a calculator so you guys can see this. I think you can see this when I switch over. Let's see here. There it is. Okay, so in your calculator, you want to make sure you're in the degree mode, and I am typing in 3 cosine of 47 degrees. Okay, we got 2.046. So go ahead and write that down, 2.046. And let me type in the other one. We had 3. Oh, come on. 3 sine 47. Okay, 2.194. So I'm going to go back to our notes next and jot these down. So x was 2.046 and y was 2.194. Putting that all together for the rectangular complex number, z equals x plus yi, we've got z equals 2.046 plus 2.194i. Okay, well, we just did a series of problems where we were provided the complex polar numerical values and we were converting them over to complex rectangular form. So that means we're going to be ready to do the opposite next. So here, our goal is to have polar form for the final answers. Remember, that would be z equals r cis theta when we talk about complex polar form. Now, we'll have particular formulas that will help us out as we want to convert. So what we want to remember is that r equals plus or minus square root of x squared plus y squared. And anytime we want to find theta, we always rely on tangent to help us do that. So theta equals inverse tangent of y over x. Okay, so just to keep it simple, let's let theta be in degrees. Okay. All right, so let's give this a try. So remember our formatting, our rectangular complex form, z equals x plus y I. So what I want to be able to tell is what x is. So x is square root of 3, and I can also see that y is a negative 1. Once I've identified those, then you're just going to be plugging them into the formulas to find what we need, meaning r equals plus or minus square root. Every time I substitute, I always use parentheses to make sure I don't make any silly sign errors. So radical 3 quantity squared plus a negative 1 in parentheses quantity squared. So r equals plus or minus square root of 3 plus 1. We get r equals plus or minus square root of 4, which is simply 2. Okay, then using our formula to calculate theta, theta equals inverse tangent. All right, so theta equals inverse tangent. Remember, it's y over x. We have negative 1 over square root of 3. I think it's worth our while to go ahead and rationalize that. That resembles unit circle information. And when I do rationalize it, I know it definitely does. So inverse tangent is something negative. We'll be looking at quadrant 2 or quadrant 4. We're going to be working in degrees, so that would be corresponding to 150 degrees or 330 degrees. Okay. Now, when we are writing down an answer, we actually have possible answers. You technically only need to provide one for homework or quiz or a test, but I just want to make sure you realize about the possibility of multiple correct answers. So one of them could be Z equals R cis 330 degrees. The reason is how you can check yourself. Go back up to the rectangular ordered pair. Notice the X value is positive, the Y value is negative. That is representing quadrant 4. And so if I'm sorry, I wrote R, I meant to write 2 there. Z equals 2 cis 330 degrees. So what I'm checking is to make sure my complex polar form also represents the same quadrant that the original problem does. So remember, 330 makes you go to quadrant 4, and a positive R value makes you stay in quadrant 4. So I'm making sure those quadrants agree, and they do. Okay, let's go ahead and jot down another one. I'm going to put or. You might have possibly had Z equals, if you wanted to use a negative R value, so negative 2 cis 150 degrees. And remember how you would be checking that. 150 degrees makes you land in quadrant 2, but the negative R value makes you move to quadrant 4, the opposite quadrant. And so now that agrees with the original problem. Okay, there's some other pairings we can do, so I'll just put or ... but there's a couple of correct answers for you to compare. All right, let's try number 2. We have Z equals negative 3. So again, remember what we want to do is compare this to Z equals X plus YI, and just force yourself to write down what is X, and I can see that X is the real number, negative 3, and Y is technically 0 if I put in my placeholder there. Okay, once I have determined that information, then I'm going to go ahead and start my calculations. R equals plus or minus square root of x squared, so negative 3 squared plus y squared, 0 squared. R equals plus or minus ends up being 9 under the radical. 9 plus 0 is 9, so R equals plus or minus 3. Okay, now for theta, remember theta is equal to inverse tangent of y over x. Our y value is 0, our x value is negative 3. So theta equals inverse tangent of 0. And that actually happens at 0 degrees. That also happens at 180 degrees is when that takes place. So now, again, I'm going to label this as possible answers because they are not the only correct answers. So one of those could be Z equals 3 cis 180 degrees. Okay, another one would be Z equals negative 3 cis 0 degrees. And think about the rectangular complex number that we started with, Z equals negative 3. That would have made us go left 3 units from the origin and not move up or down. So we want to be on that negative, what we typically call our negative x-axis, or the negative side of the real axis. All right, number 3. Again, looking for particular pieces of information. What exactly is x and what exactly is y? So x is 4, and we've got y equals negative 7. So we'll go ahead and proceed. Let's calculate the r value. Plus or minus square root of 4 squared plus negative 7 squared. So r equals plus or minus square root of 16 plus 49. That gives us a grand total of square root of 65, which you might also like to know your decimal approximation is about 8.06. Let me double check my decimal places here. .062. Okay. All right. That means theta can be found now. Theta equals inverse tangent. We've got negative 7 over 4. So we're going to need your calculator help. So I'm going to go back and type that in. Go to my Desmos Scientific Calculator real quick. For some reason, my TI calculator is not working on my laptop. That's why I'm using Desmos. So I need inverse tangent. Let's see here. There it is. Inverse tangent of -7 divided by 4. Okay, so that gave us -60.255. So remember, that is related to your reference angle. Your reference angle would be 60.26. And since it was inverse tangent of a -7/4, I want to get my quadrant 2 angle answer. So I will take, I guess, quadrant 2 as well as quadrant 4 would be helpful. So I'll take 180 minus the 60.255. This is really annoying. Okay. Write that down, 119.745. Okay, and then of course we want 360 minus 60.255. And jot that down, 299.745. All right, back to the notes. Okay, so from the calculator, we got -60.255 degrees. If I make that adjustment working with the reference angle, then we knew we had 119.745 degrees, and our other one was 299.745 degrees. Okay, so again, remember, like last time, we list these as possible answers because they're not the only correct answers. All right, so we've got Z equals, and you can use the decimal version of R or just the square root. I mean, the square root's probably easiest, and you have to write quite as much. So if I use positive radical 65, I would pair that with cis 299.745 degrees. Because what I'm noticing is that rectangular complex number is going to where? Right, so that's positive, and then negative down, so that's quadrant 4. When I examine that, 299.745 degrees is in quadrant 4. Positive R value makes you stay there. Okay. Another possible pairing of information is if I use my negative R value. And sorry, let me make sure that looks better. Let's start fresh. Square root 65 is 119.745 degrees. Okay, we are now ready to start looking at operations. So there's some patterns and things that happen. We're going to multiply complex numbers in polar form. What you do is multiply the R values together and you add the angles. Division is kind of a similar type of pattern. You will divide the R values and subtract the angles. So you might even think about how multiplying and adding team together when we utilize exponent rules back in Algebra 2. And likewise, when we divide and using exponent rules, when we're dividing with the same bases, our rule is that we subtract the exponent. So dividing and subtraction go together just like multiplying and addition do. All right, so it says write each product or quotient in polar form and rectangular form. So the polar form is the quick and easy part. We're going to do exactly what it said. So number one is multiplying. So we multiply the R value. So 3 times 4 gives you 12. And let me go ahead and identify what we're doing. Complex polar. So 3 times 4 is 12. Keep the cis. And then we add 165 plus 45 degrees gives us 210 degrees. Okay. All right. Then after that, we can go through the process for complex rectangular. And remember what formulas we need. X equals R cosine of theta. Y equals R sine of theta. That will help us out. So we'll plug in what we know. R is 12 times cosine of 210. So 210 is off the unit circle. That makes 12 times negative radical 3 over 2, giving us negative 6 square root of 3. Likewise, now we'll find y. Y equals 12 times sine of 210 degrees. That is y equals 12 times negative 1/2. And we have negative 6 for y. Putting that all together into our complex rectangular form, remember z equals x plus yi is our format. So z equals negative 6 square root of 3 minus 6i. Okay, let's go try another one. This one is set up as division. But remember what we'll do. Let me scroll back a little bit further. You will divide your R values. So our R value is going to end up being the fraction 3/4. So z equals 3/4 cis. And now we're supposed to subtract the angle. So we need to take 160 degrees minus 45 degrees. And that will give you the result of 120 degrees. Okay, and then our process for complex rectangular, we just did one of those. So let's find the value of x, which would be 3/4 times cosine of 120 degrees from the unit circle. Cosine at 120 is negative 1/2. So we get x equals negative 3/8. Okay, now we'll find y. Y equals 3/4 sine of 120 degrees. So y equals 3/4 times positive radical 3 over 2, giving us y equals 3 radical 3 all over 8. And then we can put that together. Z equals negative 3/8 for x plus 3 square root of 3 over 8 times I. Okay, so that's just our basic steps that we can utilize to multiply complex numbers and divide complex numbers. So we just did one of each. There's nothing really any different we can do to make that harder for you. You'll just need to make sure you pay attention to directions if they request complex polar form or complex rectangular form for a final answer, or maybe they want you to do both, like how we did in notes. Okay, so the next thing is a shortcut. When we work with powers of complex numbers, de Moivre's theorem helps us out a bunch to work with a pattern. So if we have a complex polar number, then it says z raised to a power is equivalent to the r value raised to that same power. And notice what we're doing with theta. Theta is being multiplied by whatever that number is for that power. So for example, if I want to find z to the 4th power, then my theorem, de Moivre's theorem, is saying I can simply take, and I'll document z to the 4th equals 2 to the 4th, my r value to the 4th power, cis, and then I would take 4 times the angle that's already there, 330 degrees. So z to the 4th equals, I know 2 times 2 times 2 times 2 is 16. That would be cis 1,320 degrees. And then one thing they like us to do is actually simplify the angle. Until that angle is between 0 degrees and 360 degrees. So technically, just take 1320 and start subtracting 360. I think we can subtract it out 3 times. Let me double check. So 1320 minus 360. The first time is 960. The second time is 600. Subtracting it the third time, we get 240. So 240 is definitely between 0 and 360 degrees. Therefore, the simplified answer, we've got z to the fourth equals 16 cis 240 degrees. Okay, so z to the fourth wasn't a huge power. We could probably have done that by hand. However, when you raise that to a much larger power, it is more convenient to definitely use de Moivre's theorem. Okay. So let's see here. Here's an example of a crazier power. We have a rectangular complex number given to us, and it's raised to the 10th power. So when you encounter this type of situation, what you want to note to yourself, it is easier to work with a complex polar number. So remember, z equals r cis theta. So we want to change the format. So we're just going to convert first over to the z equals r cis theta formatting. Then we will apply de Moivre's theorem afterwards. Otherwise, if you left this in rectangular form, you would have to be multiplying radical 3 minus I times itself 10 times. Nobody wants to do that. That would be a lot of ridiculous work, just time-consuming and tedious. So here we are. So if I need z equals r cis theta, I'm just going to write down. I know I can see that x is radical 3, y is negative 1. And so then we would have r equals plus or minus square root radical 3 squared plus a negative 1 squared. That's going to give us a grand total of 4 underneath. So we got plus or minus 2 for our r value. Theta is equal to inverse tangent of y, which is negative 1 over x, radical 3. Feel a little deja vu, like maybe we did this exact expression in our notes earlier. So if you want to, you can flip back, take a peek. So negative radical 3 over 3. That rings a bell for unit circle. So options for theta are 150 degrees for quadrant 2 and 330 degrees for quadrant 4. So now what we'll do is put this all together. And what I'm making sure I'm paying attention to would be the fact that radical 3 and that negative 1i, that is positive comma negative, that is quadrant 4. So if I'm trying to make sure my polar information is referring to quadrant 4, then that would be z equals, I'm going to go ahead and use my positive 2 cis. I'm going to pick the angle that's already in quadrant 4. Whoops, I meant to make a degree symbol. Oh, no, wait, there we go. Now I've got it. Okay, so from here, then I just pay attention to the kind of power. If I want z to the 10th, then I need to take the r value to the 10th power, and I need to take 10 times the 330 degrees. Okay, so 2 to the 10th, if you type that in your calculator, that ends up being 1,024. And of course, 10 times 330 degrees is 3,300 degrees. And like I showed you in that last problem, subtract out 360 until we get an angle value that is in between 0 to 360 degrees. So I'm just writing myself a note. We're going to simplify theta So once we do that, that should give us z to the 10th equals 1,024 cis 60 degrees. All right, our last few examples, a little bit of review from how we started chapter 8, but never hurts. So you might even just pause the video and try these and double check your answers at the end. Make sure you're still in good shape with these. So, and afterwards, check, please. So remember I, we define that as square root of negative 1. I squared is technically I times another I, just utilizing exponent rules, which means square root of negative 1 times another square root of negative 1, giving us negative 1. For I cubed, we could take I squared times I using my exponent rules. I'm going to use my last answer, negative 1 times I. So usually the simplified version of I cubed is negative I. For I to the 4th, we can take I squared times I squared, which is negative 1 times negative 1, making a final result of positive 1. So you definitely make sure you have these memorized. And you can use exponent rules to always help you generate them again if you're having trouble remembering them. Otherwise, hopefully you can remember these. They're just 4 pieces of information, not too bad. Okay, some other operations with these. That first one here, this is just representing FOILing with our multiplication. So I've got negative 20 plus 15i plus 8i minus 6i squared. So that gives us, once we put some like terms together, I've got negative 20 plus 23i. Anytime we have I squared, we're replacing that with negative 1. So that would make positive 6 out of that. Negative 20 plus 6 gives us negative 14 for our real number, plus 23i for the complex number. And remember, real followed by the complex term when we look at the format. Our next one is this plain old distributive property. Distribute that negative 3i to both terms inside the parentheses, so negative 6i plus 6i squared. Remembering, anytime you have I squared, we replace it with negative 1. So negative 6i minus 6, usually rearrange that as negative 6, the real number, minus the complex term, that's 6i. Okay. All right, our last 3 here that we have, determining the simplest polar form of each expression. This is going to let you think through de Moivre's theorem, applying that. So I recommend pausing and trying them on your own to make sure you're getting that, and then restart the video to check. Okay, so as you're reading the prompt, I did put in bold letters, make sure you remember to do simplest form. That means that theta at the end needs to be between 0 to 360 degrees. Okay, so on number 1, I would take and raise my r value to the 4th power, and then 4 times the angle value of 10 degrees. So 3 to the 4th power is 81. And of course, 4 times 10 degrees is 40 degrees. It's done. Number 2, I need to take the r value 8, raise it to the 3rd power. Oops. Recopy my cis notation. And then I'm taking 3 times pi over 3. So 8 cubed ends up being 512. You're welcome to do that on the calculator if you need a little help. And 3 times pi over 3 is simply pi. All right, one more. We have the r value 2 is raised to the 5th power. Cis, we have 5 times 100 degrees. 2 to the 5th is 32. And of course, 5 times 100 makes 500 degrees. And you're going to simplify that 500 degrees. It's not between 0 to 360. So take out 360, and that would leave you with 32 of 140 degrees. Okay, we are going to stop there with our notes, and I will make a part 2 to 8.2 notes to talk about roots and solving polynomial equations.